briefly tell you guys what processing is all about. Okay, processing is seismic step. When I talk about processing, confirm you can see my screen and hear me very well.
Yes, you can see and hear you.
Okay, so processing is a step in exploration that people don't talk about, especially in Nigerian our university system. So it's likely you go through your school and you never hear that there's something they call seismic processing, especially if you study geology. You only hear about seismic data and maybe acquisition and interpretation. So without processing, you can't do anything with the acquired seismic data because the data in itself is not interpretable after acquisition. So the data has to go through some processing steps. So I'll be fast about it. I don't think I can conclude the slides today, but I think we'll take another class probably tomorrow so that we'll round it up and see how we'll take care of the rest of the lecture series on interpretation. So you just have to flow with me fast and understand what talking about. So objective still remains the objective for the program mentorship cycle. Okay. And the most important to me is that at the end of the day, if you find yourself in an acquisition company, processing company, or an exploration company that is into interpretation, you will know what to do and you will not be totally lost, even if you're a newbie in the industry. So we'll talk about processing. So I'll be fast about it, as I said. And I just pray you will flow with me. So for our processing of seismic data, we'll take this outline, okay, from introduction to the basic processing workflow, and out of the workflow, I'll take you through some of the method processing steps. So introduction, okay. So as I said, seismic processing is a step that involves mathematical operations on your acquired seismic data. So you do that on the workstations and in what we call the seismic processing centers. And your aim is to make the seismic data become interpretable. So the acquired seismic data is not interpretable in any way. You cannot identify faults, you cannot identify geologic structures, fault folds, or whatever on the seismic data you acquire from the field. You remember the last time when we ended the acquisition, I told you about the acquisition deliverables. You get your raw stack sections, your raw short gathers in hard disk or maybe cartridges. So the data that they give to you after acquisition cannot interpret it. So based on what we have on this, based on what we have here, so your data has to go through from acquisition, you have to go through processing, and then after processing operation, the data can now become interpretable. Okay, before you can talk of interpretation that all of you are eager and you all know about. So for processing, there are three major processing steps: the convolution, which we call signal analysis, stacking, and migration. These are the key processing steps. Every other thing is aimed at bringing these three processing steps to a conclusion. So before you do your deconvolution, there are a lot of other processing which we can be called pre-processing steps, okay? Pre-processing steps, okay? And after you finish your deconvolution, stacking, velocity analysis to migration, you can call our post-processing steps. Whatever you do after migration, are called post-processing or post-migration steps, okay? But in all, The primary aim of doing processing is to make the seismic data become what? Interpretable. Interpretable image of the subsurface that you've acquired in the field. So this is what your raw seismic shot data will always look like. The image on the left, okay, the one here, as I already showed you during acquisition. So the processing operations brings it to what is on the right, which is a shot gather. On a shot gather to the left, and then a stack section to the right. So on the right, you have a stack section. On the stack section, you can now see what's some of the structures, what looks like a fault here, another fault here, maybe, and maybe another one here. So that's where you now start doing all your geology interpretations, okay? So as I said earlier, the raw data is not interpretable, so it has to go through processing to become interpretable. So to achieve that, one thing you also have to know is that for you to do processing, the elements of a good processing job is that one, the geometry has to be good. Okay, the geometry of the seismic process data has to be very accurate. If the geometry is wrong, every other thing you're doing is a waste of time. Then you have to have a compact wavelets, okay, which is your signal analysis. So you have to compact your wavelets. I will get to that when I talk about the convolution. And also your data has to have high signal to noise ratio. During acquisition, you acquire both the signals. We know what signals are, your reflections that are coming from geologic boundaries. These are your signals. And the signals have to surpass the noise. So your signal to noise ratio has to be high. So at the end of the day, these are your three expected, the elements of a good processed seismic data. So if you look at the image on the right, you will see that on the right, you have the upper part, you have the seismic data, which is termed the good processing, and the one below is termed the great processing. So if you look at the both of them, they are telling about the same geology story, but there is a difference in terms of interpretability of the data. So if you are not conversant with processing, it's not as if the one on top cannot yield a good interpretation, but the one below will yield a better interpretation. Let me highlight a few points for you to see. The one on, if you look at this data, the one above, which is good processing, you cannot see the faults. I'm trying to map the faults, okay, on green with a green pen. You can see a green marker. This is a fault line, a major growth fault, right? Behind the fault in this area, I have circled red, circled green. You can see the image is not very clear around there. The imaging is not very continuous, not very clear. But the one with labeled great processing below, the same fault is there, okay? And you can see behind this fault, in the same area I'm circling green, you can see event continuity. So that's a very big difference between the data bit above and the one below. So if you also look at the events, the one above, the red and the black lines, you can see the red and black lines are looking like they were drawn with a blunt pencil. For instance, this first event here, okay, where I put an arrow now. This first major event with a strong amplitude, you can see the event is looking somewhat like it was, let's say you draw it with a blunt pencil. If you look at the same event on the second one, where you have the arrow, you can see the event is sharper. Okay, so these are things you look out for. Another event on this horizon, on this zoom horizon here, you can see the event is sharp, is blurred, and the one be above, and on the stack section below is sharper. So if you look through the data, you see that, and these are important in your interpretation. You need your geologic units and informations to be well resolved. So that is it for elements of good seismic processing. So the next thing I'll look at is we already know what signals mean when we talk about seismic wave traveling. from the source point or the short point to your, hold on a bit, to your receivers. We already seen what this image is, and we already know what it is. Now, during acquisition, we get through this process where seismic wave travel and they reflect at the geologic boundaries. We all know this already. I don't need to spend time explaining that anymore. Now, after we've acquired the seismic data, we will come up with the short gather that looks like this. So the essence of me trying to explain this is on a typical short gather of a seismic data, you have both your what we call signals and the noise. And I told you the element of good processing is that it has to have high signal to noise ratio, okay? To noise ratio. So your signal has to surpass your noise. So one question that will come to your mind is, how will you now know who is signal and how will you know who is noise, which is what we don't want. So the essence of putting this slide is for me to try to explain to you how you identify your signal on a typical short gather, on how maybe a CMP gather, your short and your CMP gather, so, and how you identify your noise. So for this particular short gather that is shown here on the left, anywhere you see any event that is hyperbolic in shape, you can see the trend. That is a signal, hyperbolic in shape. And your events are hyperbolic. When I mean events, I mean signals. They are hyperbolic because during your acquisition, when you shoot the seismic data from the source, the energy travels away in all directions away from the source, right? So it's traveling to the left and to the right, and then it's reflecting on boundary A and getting to the geophones or the receivers on the left and to the right. Because these geophones are placed at regular intervals away from the source, that means the offset to the right is increasing, okay? The offset to the right is increasing, and offset to the left is also increasing. So this is known as a normal move out, NMO, okay? So increase in distance of the receivers away from the source. So if that happens, the arrival time of the seismic wave from the source to the different receivers will increase away from the source. So that is shown, exemplified in the next slide, where I try to depict here. If our source is here in the center, okay, and you
Just
shoot
came
your
inside. I don't
side,
know what did you right? I just listed everything I did.
please, co-host, mute
I
every
just
other
listed everything I did.
person.
Now to talk about.
So if the source is at the center and assumed there's also a receiver here, what we call zero offset receivers. For the first boundary, for this one, for this first interface, the first interface I put an arrow on, the receiver one will pick up information at assumed to be maybe 0.4 milliseconds. And the receiver one to the other side will also pick up the reflected seismic wave at 0.4 seconds. The same thing happens to the receiver two. So the receiver one is assumed to be here, receiver two, receiver three, and so on and so forth. So when you shoot your seismic data from here, or your seismic from here, your dynamite is detonated here. The seismic wave will travel through the first interface or the first boundary, and these receivers will pick up this information at different times. And their times and the time of arrival of the seismic wave to the different receivers will increase as the distance of the receiver increases away from the source. So this is what is known as what? Normal move out. NMO, normal move out. So because the distance is increasing away from the source, and you remember your receivers are placed at regular intervals, maybe 50 meters apart. If you plot a graph of time against offsets on the x-axis, you have your offset, your offset, and on the y-axis, you have your time. So you put your time here, you put a graph of time. I'm sure all of us know how to plot graphs. And then you put your offset, which is your receiver point, and they assume that the source point is in the center here. So you put the receiver point away from the center. If you do that, if you plot these values are presented here on a graph like this, you will get a hyperbolic shape. Okay? I know you will not have time to do that in the class here. So I want someone to take a picture of this slide and share that in the class. I will exit screen sharing so that you can take your picture, discard, and then come back. So somebody should, moderator should please take a picture of this slide. So I'd like you to plot this graph for me, which is in depicting the arrival time of your seismic wave to different receivers on different boundaries. We already know how reflection occur when it comes to, so we are not dealing about that. So you can also interpolate, calculate anyway, what the arrival time of the seismic wave will be on boundary C. Remember, we are coming from here. This is boundary A, boundary B, and boundary C. Boundary A, B, and C. If you like, you can add a D to the graph, and that's up to you. And all your plottings has to be on the same graph, okay? All your plots has to be on the same graph. So whatever you plot boundary A on the same graph, plot B, plot C, all of them on the same graph. So you get a hyperbolic shape at the end of the day. And that is what your signal, your seismic signal looks like. So anytime you're hearing signal to noise ratio, remember my objective here is to get you up to speed on the basics of the seismic method, acquisition, processing, interpretation. So anytime you're hearing seismic signal, it means your reflections that are coming from your geological boundaries. And as in geophysics or in seismic, in geophysics terms, acoustic impedance contrast boundaries. So on your stack section, they will have this hyperbolic shape. Okay, so you can see these ones that I'm tracing with red line. These are your signals. So anything that is not hyperbolic in shape is not a signal. Anything on your seismic short gathers that are not hyperbolic in shape, on your short gather, on your CMP gathers, anything that is not hyperbolic in shape, they are not signals. So every other event, you can see this other event that is like this. It's not hyperbolic in shape. It's looking like an isosceles triangle. This is not a signal. Whatever, this one that is here is not a signal. They are all noise. So your seismic data is laden with abundance of noise and signals from the subsurface rock boundaries. So the aim of processing is to remove the noise and get the signals, and then use the signals to generate an image, interpretable image of the subsurface where the reflections came from. So having armed you with this information, we can now further proceed, because I don't want you to get confused as we proceed, or when you hear signal to noise ratio, you don't get what they are all about. So for a typical seismic processing workflow for land seismic data anyway, this is what it looks like. So when you load the data, you reformat, there's what we call seismic formats. I'll talk about that in the next slide. And then update geometry, you can do trace editing, statics correction. So this conventionally what a simple processing workflow looks like. There could be a lot of other processing flows that will come in between, but these are primary workflows that cannot be escaped. So if you look, you can see the convolution has a different color, stacking, and PSTM, what we call pre-stack time migration. So migration can be in time and it can be in depth. I'll talk about that when I get to migration. So this is your typical processing workflow. And for every processing workflow, there has to be quality check, QC. So what we term the supervision, okay? So any step you go through in seismic processing, it has to be quality checked, QC. And so each processing flow has its own way of being QC'd to know whether you did the right thing or the wrong thing, or you didn't get it exactly accurately correct or whatever. So we'll start looking at the workflows one after the other, and I'll see how far we can go today. And then, so data formats and geometry updates. So when you get your seismic data from the field, the data is usually stored in this, what we call the tape cartridge, okay? So this is exactly what the tape cartridge is. This is the back view of the tape cartridge, and this is the front view. Sorry, this is the front view, and this is the back view, okay? So the tape is like a floppy disk. Do you remember? If I don't know if any of you remember floppy disk, okay? It's a magnetic tape. So inside it has a reel of magnetic tape inside. So on the front part of it here, it will be properly labeled. So you have a sticker or a paper that stick to it containing the data information. Excuse me for 1 minute, please.
Okay, sir.
Please, your voice. So sorry about that. So your data comes in this tape, call it the tape cartridge. So it's not just one tape, it will come in dozens of this tape, okay? So many of them, but this is typically what the tape looks like, okay? Can come in different color. The tape can be black in color, can be red as shown. Can also be sent to you in hard disk. All of you know what external hard disk is. And the third figure in this image is what we call the tape copier or the tape reader. So this machine, this small machine, is where you slot the tape to copy the tape. So the machine can come in different sizes. This is a typical, the smallest, about the smallest size, and you can see in when you walk into an office where they are doing processing or tape storage. So the seismic data can come in tapes or hard disk, as we know, and you can also store in cloud. We all know that already. So from the field, your seismic data will come in two formats. It will come in two formats. It will come in the SegD format, and it will also come in the SegY format, okay? Most times, the SegD format, it will definitely come in the SegD format, and then it will also come in SegY format. So before you start processing your seismic data, you typically make a copy, back up your data somewhere. You know, all of us know what data backup is. So you back it up. Either you copy from the tape to your computer, or sorry, to your server. And then from the server, you start working with the data, and you have the original copy in the tape or in the hard disk. Okay, so that's basically that. So the question will now be, what is SegD? What is SegY? Okay, SegD, well, we know what all of us know what SEG means. Society of Exploration Geophysics data D type, and Society of Exploration Geophysics data Y type. So that's the format. So for the SEG-D, they are the unidented shots, while the SEG-Y is the indented shot gathers. So what is contained what is contained in the hard disk or in your tape is short gathers, okay, of the acquisition that was done in the field. And the short gathers will come either as SEG-D or SEG-Y. And the SEG-Y is known as your indented shots, okay? Okay, they have identity information, while the SEG-D are the unidented shots. They do not have identity information. So what is then the identity we are talking about? Identity and non-idented, or we say idented and non-idented. What do we now mean? When the seismic data is acquired in the field, the seismic data, alongside the data, you get the SPS file. If you go back to the slide I sent to you on acquisition deliverables, you also see what this SPS, okay? So this SPS stands for Shell Processing Support, Okay, it's a data that will be sent to you usually as a notepad. Okay, come as notepad data. All of us know what notepad is. So it comes as notepad, most times at notepad, note files rather, note files or notepad. Okay, note files. So inside the SPS file data, or SPS file as we call it, you have the source file or the receiver file and the cross-reference file. So you have the arrow file, or call the receiver file. So within the receiver file, you have every information about the receiver. You know what I mean by receiver? The geophones, the hydrophones, the nodes, whether it is OBC or OBN, whatever nodes, the receivers that we are used for the acquisition, every information about the receiver will be stored in the receiver file. And then it also have the S file, where you store information about the shots. Remember, in acquisition, for instance, for land acquisition, you put your receiver lines, and across the receiver lines, you have your short lines. Okay, you have your short lines. So as your shots is being fired across the receiver lines, you are taking information about the source, each of them, be it vibro size, be it dynamite. So this is your short line and whatever. You measure, you record the short information. So into the source file or the S file. Then you have the X file or the cross-reference file. In this file, you record information that gives you the relationship between the receiver and the source. It's a file that gives you the relationship between the receiver and the source. So you know that during acquisition, you have your source here, you have a receiver here, and then you have a particular geologic boundary. The seismic wave travels to the boundary and is reflected to this receiver, right? Okay. So your S file is carrying information about the source. Your arrow file is carrying information about this receiver. Your relationship file is carrying information about the travel pathway of this seismic wave that is recorded here. So it gives you relationship between your X and your R in terms of the travel path of the seismic waves, okay? So that's it about that. Then you can also have your comment file where you have comments like mostly the header information about these different files, the acquisition dates, acquisition information, and all that. So that's typically what the SPS is. So it is this SPS file that is used to do your geometry updates, okay? So to update the geometry of the acquisition, you need the SPS file after you've gotten your seg-D or maybe your seg-Y. Now, these informations that I've identified that are included within the SPS file, and this is typically what an SPS file looks like. This is for a source. It comes like a spreadsheet in Notepad or in Note files. So this is what the source file will look like, and this is what the relationship file will look like. So typically, when you have your seg-D and your seg-Y, okay, files, these are both the same file, the same, your seg-D and seg-Y data, seg-Y, they are both the same data sets coming from the field. They are containing both the same information, but the difference is that these seg-D are unindented, meaning the information contained in the SPS file are not inside this data. So these data are just the raw seismic data. And while the seg-Y file are the seismic data that already have the SPS information written into them. So they have geometry information written into them. The way I described it to one of my interns was that the seg-D is like you bought a car. Seg-D and the seg-Y is like you bought a car, okay? Both the same car, made by the same company, the same year. So you have, let's say, Toyota Corolla, the same Toyota Corolla. If you don't put a plate number on that Toyota Corolla, it's still synonymous to that Toyota Corolla being a seg-D data, okay? It doesn't have a plate number. So if that car is stolen, there's no way you can identify that car when it's stolen by anybody because it doesn't have a registration number, right? But if that car is registered and you have a plate number to it, that car is synonymous to a seg-Y file. So the car is still the car. But if you register the car and give it a registration number, it becomes a SegWire. Okay? So the SegD and the SegWire are typically the same seismic data. No difference in terms of subsurface information, but the difference is that the SegD data is unidented. It doesn't contain the SPS information, while the SegWire contains the SPS information. So during your geometry update, you need the SPS file to do your geometry updating of your seismic data. So if peradventure you're in a company and you have a SegD data and they want to process it, you need to give the processor the SPS file. Have that at the back of your mind. You have to give the processing company the SPS file and the SegD file. But what happens if you have the SegWire file and you don't have the SPS? Let's say maybe they acquired the data 20, 30 years ago. Due to carelessness, they've lost some information, so maybe their SPS, they don't know where it is. It simply means that the processing company can extract the SPS information from the SegWire file, but they can never ever extract it from the SegD file. So from the SegD data. Okay? So if you have an SegWire seismic data, you can extract the SPS information from it because it's already been idented. It has those identities written into it. But for the SegD, it's not idented. There's nothing anybody can do. There's no magic that anybody can do until you find this SPS. Your processing flow cannot continue. You are stuck. So that is that. Now, when you finish doing your geometry updates, your results will definitely look something like this. So this is your source and receiver map to the left. So you can see the blue line. Sorry, I didn't put a legend. I'll update this before I send. So your blue line is showing your receiver line. So your receiver line where you have your different receivers. While the red lines and the red dots are showing your short points. So this was what you get after your geometry update, the receiver and the source map. You also get a fold map. So if you're looking at this data, can anybody tell me what the highest fold in this data is? Like I explained fold a lot during our acquisition. What's the highest fold number within this data?
50, around 51 to 55. Wait, let me see. No, around 45 to 50.
Yeah, 45 to 50. So that's the nominal fold of the data. Okay, I've explained fold. If you can't remember, go back to the last slide I sent. So you get a fold map like this of the survey area. So these are the informations that will come up after you do your geometry updates. There are more, like you can also get your receiver map showing only the receiver, source map showing only the source, and there are different elevations. So I don't want to bother you with all those ones. So after you finish, I remember I told you every processing step, you must have a quality check or QC. So the first thing you do after doing geometry update is that you must quality check it, and there are two ways to do that. You have the linear move out and the mute method. So they are the two ways. For your linear move out method, you stretch out your short gather. You already know what short gathers is, where we have your short gather. So you stretch them out the way it's looking on the screen by your left by using a linear mover velocity. So you stretch out these short gathers and it will appear something like this, like what you have on the screen. The next is your mute. When you mute, apply a mute on the seismic data, it will look something like this as well. You have your short gather already. On top of the short gather, you have your mute line, which are these green lines that are showing. So you can see that the lines are following the alignment or in alignment with the short gathers, okay? You'll see they are following the trend of the short gathers. So if there is an error with your geometry update, the mute line will not follow this trend. That's your linear move out. These short gathers will not flatten out. They will never flatten out, never. So you try different mutes, linear mover velocity, and you're not getting them to flat out. And when you apply your mute, you will find out that some of the mute lines will not align with your short gather. So instead of having an organized mute line like what we have on screen, you can have something like this. You can have this one being double of itself. or you can have one that is passing in between two different receiver lines or doing something like this. So it will never be regular, it will never be orderly, and that is your effect. So when it's regular and orderly as the one I'm showing on the screen, is a pointer that your geometry update was correct. Okay, so the next thing you do after geometry updates, and before I proceed, geometry update is the first step in seismic processing. It must be right. There is no room for error in geometry updates. So what geometry updates also do, let me further explain, is that you're placing all your receiver and your sources exactly where they were on the subsurface, on the surface. So every information they are going to pick from the subsurface is coming from exactly where it is on the subsurface. So for instance, this is your surface, this is the subsurface. If you have a fault here, you're identifying that this fault is on this particular location in the subsurface. If your geometry is wrong, if your geometry update is wrong, okay, for any reason you did it wrong, it means that in the subsurface, this particular fault you have shifted it to maybe this position. And so the implication is that during interpretation, when they interpret this seismic data, they will be interpreting that this fault is here, whereas in reality, it is where the green one is. So if you go and do your drilling of your well, for instance, you go and drill here, and when the driller gets to this depth, they'll find out there's no structure here. Okay, what happens? This is a dry hole. In reality, the structure is here. Maybe the reservoir is here. Okay, so your well is supposed to go this way to this reservoir. But unfortunately, because you did the wrong geometry update and nobody knew that you did the wrong geometry update, even if you did every other processing step to be very fantastic, the seismic data will come out clean and well interpretable. As far as your geometry is wrong, your positions of your subsurface structures will be wrong. So you'll be having an anticline that is here instead of here. So you go and drill a well here, and then you come out with a dry hole. Okay? Well, when you drill in the proper position of the structures, you identify, you make your maybe you hit your jackpot and all that. So that is the essence of your geometry update. It is the first step and it must be correct. No room for error. So after that, statics correction. So what is statics correction? In statics correction, you're trying to correct for the effect of elevation differences in the topography of the area where the seismic data is acquired. So in the region where I acquire the seismic data, some of the geophones will be on a higher plane than the others, okay? Just as shown by my cartoon on the screen. So you can have another geophone that is up here, another one up here. So you can see that their elevations are different. So if the elevations are different, that is for elevation statics correction, you need to correct this error, okay, due to elevation difference. You can see this one now, see the elevation. So see the difference in elevation between geophone 3 and geophone 1, okay? So this error, this statics problem, it will introduce statics problem to your seismic data due to difference in what? Elevation. So the idea is that you are going to do a correction to the seismic data such that all the geophones will be marginally placed on the same level, okay? They will all be placed on the same level. So looking at that, still on the statics error or statics elevation statics correction, you can see, look at this cartoon on the right. You have your different geophones on different levels or different elevations, and you shoot your source here, okay? When the seismic waves travel and gets to these receivers, when you record them, remember what I told you to the screen, the slide I told you to take picture of, where you're going to measure hyperbolic, you are going to plot a graph and see the hyperbolic shape of your signals. So if you plot a graph of the signals for this one, remember that the receivers are evenly placed away from the source in both directions. If you look at this, you're not going to look at the trend of your event. See the way they are trending. Is this a hyperbolic shape? Any answer?
No.
So this is not a hyperbolic shape. The vents are irregular. Remember, the vents are coming from an assumed flat geologic boundary. And when they come back to the surface, they are supposed to give you a hyperbolic shape like this, something like this. But look at the trend they are giving you. Okay, so this is not hyperbolic. So it's a problem in your seismic data. And to correct that problem, you do that using what we call the elevation statics correction. Okay, so you look at the second slide. You are bringing all the receivers to this imaginary datum. Okay, what we call the seismic reference datum. So this your datum could be 0 meters above sea level, whatever. Whatever you choose, depending on the location of the acquisition and what the acquisition was carried. Mostly for Niger Delta, we normally use 0 mean sea level. All of us know what is mean sea level. That is 0 meters above sea level. So we are assuming that all these receivers will come down to be on that imaginary boundary. Okay, so we are bringing all the receivers down to these points. Okay, on this imaginary reference datum. Okay, so when you plot a graph of your receiver, your arrival time against offset, you can see that this one will have a hyperbolic shape. Does that make sense?
Yes, sir.
Okay, so that is what we mean by statics correction in terms of elevation statics correction. The next statics correction we will talk about is what we call the refraction statics correction. Okay, what does this do? In your acquisition, in land seismic acquisition, you have your weather layer. Okay, if you've been to the field, I forgot to add that slide. If you've been to the field, that picture, for instance, you find out that if this is the earth surface, the first layer is always made up of red mud, what we call lateritic for cover. So this first layer is usually red mud or laterite. Most of you have been to outcrops for your field work. If you have been to an outcrop, go back to your picture you took in the field and look at that outcrop. The first layer is usually made up of lateritic cover like this, which is the red layer that I'm showing here, which is here. Okay. Now, this layer or the lateritic cover, in geology, we call it the weather layer, okay, or the weather thickness or weather layer. And in geophysics, it is called the low velocity layer, okay? The geophysicists term it as the low velocity layer. Why? The velocity of this rock is usually low because it has undergone weathering. We all know what weathering is in our elementary geology classes or basic geology classes. And then you remember that when we were talking about the seismic method, I told you that we have two types of seismic method, the reflection seismic. If you have forgotten, go back to the slide. Reflection seismic and the what? The refraction seismic. Okay. So what happens in refraction seismic is that the seismic wave travels through the boundary between the rock layer above and the one below. So during acquisition, the seismic energy or seismic wave, normally in land seismic acquisition, they drill the short hole. I explained this during our acquisition class. And then put the dynamite inside the short hole, except if it's a vibroseis, then the truck will be on the surface. So if it's a vibroseis, the truck will be here. So if it's a whether dynamite or vibroseis, the point is the seismic wave, when it travels through this rock, for instance, if the seismic wave travels through this rock, it will pass through this low velocity layer, the LVL, okay? And this LVL will slow down the seismic wave. And then on getting, because the velocity in this layer is smaller than the velocity in this layer, there will be a refraction at this boundary, and the seismic wave will travel at this boundary and then go to the receivers. Now, when the seismic wave travels and gets to this boundary, it will refract. It will also continue to transmit as shown. That's if you're using your vibroseis truck. If you're using your dynamite, they normally drill short holes. The idea is that they want to avoid the low velocity layer, and they put the dynamite at the base here and shoot. So the seismic wave will travel through the layer 2, get to the interface between layer 2 and layer 3, for instance, and then reflect and still come back. When it's traveling back, it will still pass through this weather layer. And what will happen? Because the velocity of the rock in this weather layer is low, the seismic wave will be slowed down. There will be a slowing down of the seismic wave. And to correct that effect, what do we now do? The geophysicists, they use the refracted waves, because as the velocity in layer 1 is smaller than the velocity in layer 2, some of the wave will travel on this boundary. I'll use a green pen this time. Some of the wave will travel on this boundary, and they are your refracted waves, okay, and get to the receivers. These are your refracted seismic waves before they go to the receivers. So the idea is that you want to correct the effect of this low velocity layer on your seismic data, because this low velocity layer slows down the returning seismic wave. Even if you're using dynamite or vibrosis, it will slow down the seismic wave as it's coming back to this receiver. So if the seismic wave is supposed to return to this receiver at maybe 0.4 milliseconds, okay, it's going to return to this receiver at maybe 0.35 or maybe 36 or maybe whatever milliseconds. Why? This layer has slows down the velocity of the seismic data wave, because it's a low velocity layer. So you need to eliminate the effect of this low velocity layer in your data. So to do that, we use what we call the phase breaks. Now, these refracted waves that travel at the boundary, and I'm shading as green, and then going to these receivers, they are very fast. So before your seismic wave will do your two-way time from the short points to the boundary and back to the receiver, which is your two-way time. So before the seismic wave will get to it at about 0.4 seconds, the one that is refracting, that went through this boundary, would have gotten to the receiver at maybe 0.1 milliseconds, okay? So the first thing you see on your seismic data is the refracted waves, what we call the head waves. We call it head waves, or as shown here, head waves, or your phase breaks. We either call them the head waves or the phase breaks. What happens? They are your refracted waves, and they are the first to arrive at the seismograph, on your seismographs or your seismic data. So this is your refracted waves, the part I'm showing on red, your head waves or your phase break, okay? So during processing, the idea is to identify these phase breaks. If you're able to identify the phase breaks, okay, you can then eliminate or thereabout model what the weather layer is like, and then eliminate what the weather layer is from your seismic data. So the first break, which is the onset, we first of all pick them out. Oh, it's a very tedious processing step. It's quite a tedious task if you have a lot of data, because you're going to do them shot by shot. So your first breaks will appear this way. So sometimes they will be good, sometimes they will be bad. So this is typically what a good phase break looks like, okay? And we also have phase breaks that are not very good. If you look at this other part, this one is not too good. This one is also not too good, not too clear. The environment of acquisition can affect the quality of your phase break, and also the source. If you use vibrosize, your phase breaks will always not appear very good. Look at the vibrosize source, the one here. But if you use your dynamite, they're always very good. Your phase breaks are always coming out good. So for land seismic acquisition, the idea is to map this phase break, and this is what it's like to map the phase break, okay? You pick out this phase break. You look at the parts that have been marked with red. So if you look at the image on the left, this one, you see that the first arrival is distorted. Okay, it's looking distorted. But by the time you finish picking your phase break and you do your refraction status correction, the image on the right is what you get from the one on the left. The event becomes what? More strengthened. So that is the idea of your refraction statics correction. Also, I think this will show it better. This is a typical first break that has been picked. If you look at this, you see the red points. Okay, you can see that they are quite looking irregular. Okay, they are looking irregular in terms of strengthening out. So if you go to the next slide, you see after your statics correction, I don't know if you're seeing the changes. You have corrected that effect, the slowness in arrival time between caused by the low velocity layer. So I don't know if you saw the change before, after, before statics correction, after statics correction. So you're correcting for the effect of the low velocity layer. That is why you do your refraction statics correction. And when you do elevation statics correction, you're correcting for the effects in the difference in topography on the surface during acquisition. So this typical stack section before and after statics correction. Before statics, that's after you've done all your statics correction, both elevation and refraction. After, before, after, before, after, before, after, before. Somebody's chat is up. What is that? Am I the only person that's not seeing the screen? Bolaji, can you see the screen now?
I'm seeing the screen.
Are you
Yes,
seeing
yes,
changes?
yes, now I can see it now.
So what are you seeing on the screen? The title on what's on the screen?
Refraction statics correction.
The subtitle, please.
Stack section before statics correction.
Can you see now when I change to the next one?
I don't really notice any change.
What are you read the subtitle again?
Stack section before statics correction.
So you have a lag.
Okay, I'm seeing it now.
Read it again.
Okay, this stack section after statics correction now.
Okay, so I don't know if your lag will allow you. I will change before and after. I will be switching the slides so you see the changes before, after, before, after. Did you see any change?
Okay.
Watch my screen again. Before, after, before, after, before, after. Any changes? Did you see any? Did anybody notice any change? Let me know if it's a general issue. I'm not hearing you, Kudus. It seems your network is very bad. Can any other person speak out?
Yeah, I can see it.
Sir, I'm with you, sir.
Okay. Any other person? I need a third opinion or fourth opinion, please.
Yeah, I can see it. Stack section after.
Did you see before, after the changes?
Yeah, I saw before, after. Yeah, I'm seeing it before now, after
Okay.
now.
Okay. So Kudus is your network, please. So this is typically what you expect to see when you do statics correction. This is your stack. Before is the stack section after your geometry update. After is the stack section when you finish your statics correction. So you can see improvement in event reflection continuity. Okay, improvement in event continuity after your statics correction. So if you look on this where I put the arrow, okay, or the area that I'll circle. So you can see before, after, before, after, before, after. So the events are coming out better after statics correction. If you also look to the right, the part I'll circle on the right, okay, so look at that area before, after, before, after, before, after, before, after. So that's the effect of your statics correction. So the aim is that it improves your event continuity, corrects your any statics error due to elevation differences and low velocity layer effects. Okay. So the next thing we'll look at is your noise. noise. You remember your seismic data, element of good seismic data is that you have to have high, someone please, who is not muted, please mute. Okay, so the signal to noise ratio has to be high. Who is speaking? So signal to noise ratio has to be high. And so your signal to noise ratio has to be high. So that's the element of good, one of the elements of good processing. So a very key processing step is noise attenuation. Okay. So there are several noises in your seismic data. Remember, during acquisition, you acquire both your signals and your noise. So there are different types of noise in your seismic data. And excuse me, at the stage of signal to, noise attenuation, you have to identify the noise in the data, understand the characteristics of the noise you've identified in terms of its property, and then attenuate that noise. So noise in your data are classified into random and coherent noise. Random in the sense that when you move on from in your seismic data from shot to shot, if the noise is continuous, okay, when you move from one shot to the next shot, the noise is there. To another shot, the noise is there. It's considered to be a coherent a coherent noise, okay, meaning you can see them shot after shot, and you are sure that they will be there shot after shot. Moreover, more or less, you are very sure that the noise is going to be after the shot is going to appear on the next shot and all that. Shots that behave like that are mostly linear noises like your ground roll, guided waves, and all that. Your reverberations and your multiples. And your random noise are noise types that are random within the data. So you don't know where they will occur. As you're moving through shots, you can come out to a particular shot and you see that noise. When you go to the next shot, the noise has disappeared, it's not there. So it's peculiar to that particular shot or peculiar to a particular region during the acquisition and all that. They are mostly caused by environmental factors and instrument failures and all that. So looking at the schematic diagram on the right of a shot gather, you can see different shots. Okay, on this data, on this diagram or the shot gather image on the right, are you seeing any hyperbolic shape? I need a response. Is there anybody seeing
No.
Yeah, they are not seeing any hyperbolic shape. Good. So this data, the signal to noise ratio here is very low. Why? You have abundance of noise. You are not seeing the hyperbolic shape. The hyperbolic shape like this. You are not seeing any of them, but they are there. Okay? They are what? They are there in the data, but the noise is masking them. You can't see them because of the noise. So the signal to noise ratio is low. Okay? So you need to attenuate the noise in the data so that the signal will be boosted and your signal to noise ratio will be high. So I was telling someone sometime, it's like for all of you now, you now do pass out ceremony in school. You finish your final paper, you go to school wearing a white shirt. And on your white shirt, somebody comes to sign some signature at your passing out and all that. In the morning when you are going for your last exam, your shirt was white. So assume that shirt to be your signals or your seismic data with signals. So by the time you finish your paper by 2 p.m. and all your friends are signing out on you, your shirt has turned from white to different colors due to the markers they are using to write their names and signature on your shirt. So you have a shirt that is now stained with blue, red, green, black marker, purple self. Sometimes lipstick. They will stain it with all manner of things. Those are the noise on the shirt. Okay. So when you go back, you want to wash your shirt. What are you trying to do? You want to eliminate the stain they are put on the shirt. Even though your sign out shirt, you don't wash them and you keep them. You want to preserve the sign outs. Now, you're washing the shirt because you want to remove the stain, which is your noise, and restore the shirt to almost its original state, which was white. So that is typically example of what happens in processing. The data has the signal, which I've explained to you what signals are, and then your noise. So your noise will take every other shape except this hyperbolic shape, okay? The noise will take every other shape in the data except the hyperbolic shape. So if you're looking at the data in front of you, the seismic shot gather in front of you, you see a lot of different noises following different trends. You can see this one following this trend. They call it the air blast. You can see the ground roll noise is going this way. You can see your reverberations going this way. You can see your first break on the top, which I've explained, or your first arrival. You can see vehicular noise following a vertical motion, harmonic noise and all that, facility noise and all that. So typically, before you start your noise attenuation, you need to know what we call noise analysis, okay? So you analyze the seismic data for the noise. When you need noise analysis, you move from shot to shot and you note down the different types of noise you're seeing on the shot on your seismic data. And then in processing, you attack this noise one after the other. So it's like you trying to wash that your signer shirt and you're using a detergent that removes only red ink. So when you wash the shirts and remove all the markings they put on your shirts that were done with red pen or red ink or red marker, you wash it with a detergent that removes only the red marker. When you finish washing it, you transfer to another bucket where you have a detergent that cleans only green markers. And then after that, you move to another that cleans only blue markers. So the same way you do that in processing. If you want to attack your ground roll noise, the seismic processing software, you use the module that attacks your ground roll noise, okay? And you attenuate your ground roll noise. The next, you can now go to another type of noise, maybe your reverberation, you attack those ones. One after the other, you remove the noise step by step in the seismic data. Attenuate, okay? If it's your ground roll noise, you need to know its property. Mind you, both signal and noise are waves. Both your signals and noise are waves, and you know the properties of waves that we discussed. All are those properties. They have amplitude and they have velocity, they have frequency. Good. Your network is very poor, Bolaji. But I heard you. I heard you're trying to mention frequency. So both your seismic signals and your seismic the noise in your data have these properties. Both, all of them have properties of a wave in terms of amplitude, signal, velocity, frequency, and the rest, wavelength, and the rest. So for instance, we want to attack your ground roll noise in your seismic data. You need to analyze your ground roll noise. You need to understand what properties it has. Every ground roll noise is known to have low frequency, it has low velocity, and it has high amplitude. These are the three characteristics of ground roll noise in your seismic data. So if you look at the schematic diagram on the right, you can see the hyperbolic shapes of your signal. Okay, this is your signal with their hyperbolic shape. Okay, hyperbolic shape signals. Now, if you also look, you see the ground roll noise with their own shape that is looking like an isosceles triangle. Okay, so the ground roll noise will always have these three properties: low frequency, low velocity, high amplitude. So you need to know what is the dominant frequency of your ground roll noise. It's the measure highest velocity. Then most times you don't pay the amplitude, they are visual observations. You ignore that. So you understand that. So for a typical seismic shot gather, this is what it will look like. Okay, you have you can see your, if you look very well, you can see your signals, okay, which are hyperbolic in shape. Then you will see this ground roll noise with their high amplitude standing out firm in front of the seismic data. Okay, standing out firm in your seismic data. So you analyze this the ground roll area in terms of its frequency and velocity content. You note down the frequency, okay, in terms of hertz, and then you note down its velocity. Okay, you do the same in the area where you have your signals. Okay, this area that appears to be clean with no noise, you also analyze the signal and identify what your frequency, dominant frequency of your signal is, and your dominant frequency of your major velocity. So most times your ground roll noise will have frequency of between 8 hertz to maybe 15 hertz. That would be the frequency, but most times 10 hertz. Okay, 10 hertz. That's for your ground roll noise. Then velocity of your ground roll noise, they are always between 600 meters per second to maybe 1,000 or 1,200 meters per second. So you can see this velocity is low. But for your signal, the signals will always have frequency. For the frequency of your signals, you will always have something like 25 hertz to maybe 40. That dominant frequency to maybe 40 hertz, not your apparent frequency. I explained that earlier. So your dominant frequency will be around this number. And then the velocities of your signal, if you remember when we did the seismic method, remember the slide on velocity of different rocks, you'll be seeing something like 2,200 or 2,400 meters per second. So that will be the velocity of around the velocity of your signal. So you can see there's significant difference in property between the ground roll noise above, okay, and your signal in terms of wave property. So this one is having frequency around 10 hertz, and this one you may have maybe dominant frequency 35 hertz or whatever. So if you look at the right, there's what we call the frequency spectrum. You see a graph of amplitude against frequency on the right. So you can see that on this graph is derived from this short gather you're seeing on the left. So you can see on this graph that you have very high amplitude. Remember that I told you ground roll noise have very high amplitude. They have very high amplitude and their velocity. And what is the frequency? Yeah, very low frequency. Look at the frequency reading, around 10 hertz. So that's your ground roll noise, standing firm in your frequency spectrum. Look at it standing firm, taking the center stage on your frequency spectrum. While other waves in the seismic data 200 dB, and then other ones are having amplitude of about 50 dB. Okay, so you can see the ground roll noise, this amplitude is very, very high. So using this information, this is what you input in the software. So that is why I started by telling you about the properties of the, when it comes to seismic method, properties of the waves. As a geophysicist, you have to understand these things. So if you understand these properties of the seismic wave and the properties of your signal, if you input it, no matter the software the company is using, no matter the company you're working with, the software can change, but the fundamental principles do not change. Okay, so you impute these properties into whatever software design. It doesn't matter how they design the software will ask you for these properties. Some softwares will even ask you for the angle, this angle here, this angle theta or whatever, angle theta of the ground roll. You can see the ground roll looking like an isosceles triangle. So this angle on the top upper part of it, some softwares may be interested in that angle. It all depends on whoever designed the software. So if you put in those parameters into the ground roll attenuation model, noise attenuation module on your software and run the job, the ground roll will go out. So if you look at the stage, the data now, before, after. Are you seeing that? I need your response. Are we seeing the effect? Before, after, before.
Yes, sir.
Good.
Yes, sir.
You can say.
Okay, so you can see the noise has gone out. So you can see your data, the noise has gone out. Now, if you look on the right, look at the frequency spectrum before and after. Please let me clean all these my scribbles. Card. Okay, I'll go to, okay. So look at it again without the scribbles. Before, after. So you look at the frequency spectrum, what do you see? It has been enhanced. As the noise goes out, the frequency spectrum has enhanced. And you can see that the frequencies of every of the wavefronts, all the frequency bandwidths, all of their amplitude that was improved as well. So before, after, before, after, before, after. Then you can output the noise if you like, and this is the noise, outputted noise. Okay, so you see the noise standing on its own, removed from the data. So during processing, one way to QC if the processing was wrong in terms of the ground road noise attenuation. Are you seeing any hyperbolic shape within the noise that I was outputted? Anything
No.
looking not good. So there's no, you didn't remove the signals, because if you're doing noise attenuation, you must be careful to remove only the noise that you're interested in and not the what signal. So assuming you did this and you saw when you output the noise and you are viewing the noise, you see something like this that are looking hyperbolic, okay, that went out. It means you harmed the seismic data. You have removed both your signals and you have to go back and look and adjust your parameters. And then when you look at your frequency spectrum, like what you have here, you can see is only the noise, which is the ground roll noise, which is high amplitude, low frequency that is out. Other frequencies are now almost zeroed out. So you didn't remove other frequencies. It's only the ground roll noise, okay, that you removed. So that's it for ground roll noise. Other type of noise, I'll be fast about this one. Other type of noise in your data. Please, moderator, are we up to 6 o'clock, 7 o'clock? I don't have a clock here. What's the time?
Yes, it's 7:27.
27, so we have barely 30 minutes. Wow.
Yeah.
Oh, okay. So other type of noise, for instance, swirl noise. For swirl noise in marine seismic data is common for marine seismic data. You have the noise in your data. You can see the hyperbolic shape of your signals trending this way within the data. Okay. And then you have these vertical lines or vertical events. These are your noise, okay? And then you have this one with very sharp angle this way. They are not hyperbolic, but the angles are sharp. So the one on the middle, this is before, after you remove your swell noise attenuation, you have your noises out. So on the last one, you have a difference. So when you are looking at attending a presentation where they are doing about processing, maybe the company you are in is processing their seismic data and they are presenting, the processing company is presenting the company, sorry, it's presenting their work, okay, to the company. If you see the word before, after difference, so they are showing you that before they did this noise attenuation, this was the data. After they did the attenuation, this is the data, and this is the difference, meaning this is what they removed from the data when you had difference. That's what was extracted in terms of the noise component of the data. Okay, another type of noise that is common in seismic data is multiples. Okay, what we call multiples. What multiples are just they are seismic waves that have traveled multiple times before they got to the receiver. So there are three types of multiples. You have water bottom multiples, interbed multiples or subsurface multiples, and peg leg multiples. These are the three I showed you. There's also another one, the interbed multiple. I don't think I showed that. So for instance, you have your source and your receiver. One thing you have to note is that multiples are very common in marine seismic acquisition. They are one of the predominant noise in marine seismic data. Ground roll noise are predominant in land seismic data. You don't see ground roll noise in marine data. You see them in land data. But for multiples, you see them in marine data predominantly. You can't escape them. For They also occur in land data, but not as much as your marine data. So for your marine data, you have the water bottom multiples, okay? Now, what happens is that this is the water surface or the ocean surface where the acquisition vessel was flying. And then you shoot the seismic here. The seismic wave will travel to the ocean floor. The floor of the ocean, this part is just the water column. The water column, okay, WC. So the seismic wave will travel to the ocean floor and then travel back. Instead of going straight to the ocean floor, hit the ocean floor and go straight to the receiver, what will happen? It comes back, gets to the ocean surface and travel back down and then go back up. Okay, so it makes this multiple travel, multiple reflections, okay, or several times of travel. So it moves downwards. So instead of doing a two-way time, as we all know, two-way time, it will do more than a two-way time. It will go down, get to this boundary, go back up, come back again, and go back up, and as many times as it likes. So it can even do three-way time, six-way time, four-way time, whatever. So this is for the one that is happening within the water column. So we call it the water bottom multiples. Okay, so they will be recorded when anytime they are tired of traveling within this water column and they come back to the receiver will record them. Okay, so they record them as into the data, and they are called multiples or reverberations, and sometimes reverberations. Then you also have the one we call subsurface multiples. They are similar to the water bottom multiple. Difference is that these ones, the seismic wave traveled beyond the ocean floor into the subsurface rocks, okay? Then travel back. On getting to the surface, instead of going to the receiver, it started going back down and then back up to the receiver. So you can do that journey multiple times. You can do it at three-way time, four-way time, doesn't matter. It depends on how much energy that is doing that. So you can travel and travel from the source to the receiver on multiple locations. So we call them what? They are multiples. Another type is the peg leg multiple. So the difference between the subsurface multiple and the peg leg multiple is that the subsurface multiple are doing that between a particular geologic boundary. But for the peg leg multiple, they can do it between multiple boundaries, okay? So for peg leg, they move from the source to a boundary, come to the water surface, go back, they can reverberate back at the water bottom and go back up, or they can reflect at this boundary, come back to the surface, reflect at the water bottom, go back to the side. They can take any sequence of interest of their choices. You can't control it. What matters is that the receiver will record them. And then what happens? For instance, the water bottom multiple, if the source is supposed to record the water bottom to this receiver at maybe 0.6 seconds, milliseconds, for instance. After recording the normal travel time, the two-way travel times to this receiver at 0.6, it will still record the multiple. The multiple will still arrive maybe at 0.9 seconds. Another one may arrive at maybe 1 second. What is there? What does that mean? It is giving you information about this boundary, or sorry, this water bottom, but on multiple locations. So on your seismic data, you have the hyperbolic shape, which is the original ocean water bottom. Then another one will come. Another one will come. All of them are recording, giving you information about this same boundary. It could be a particular geologic boundary in the subsurface, but that boundary will be recorded multiple times because the wave keeps traveling multiple times. Okay, so what happens is, for instance, we have what we call surface-related multiple elimination, which is used for the water bottom multiples and near surface multiples. So how do you eliminate that? If you look at this seismic data on the left, okay, the one on the left, you see this is the ocean floor, your first arrival on the ocean floor. Now, or the ocean floor reflection, rather. You see also there's another reflection that is with strong amplitude. at this band, at this level, and another one with a strong amplitude also at this level. They are all coming from the same sea floor, which is the first part of your data. But because there are multiples in the data, if you are not experienced, you will think it's a strong event. Okay? If you look at it, you will not know that it's a noise. But looking at it, it's appearing very innocent, as like it's part of the data, because it's also following a hyperbolic shape. It's also maintaining the hyperbolic shape of your seismic signals, but it's actually a noise. So it's called a multiple. So if you look at this one of the ways to attenuate them is called one of the modules for attenuating multiple called the surface-related multiple elimination module. So this is your multiple. This module will model the multiple as shown here on the second middle panel. And then the last panel will show you so this is more like the difference, okay? And the last panel will show you after the multiple has been attenuated. So you can see before and after. You can see what is after. You can see what the short gather looks like. So this event you are seeing in the before at the middle part around 3.5 seconds. They are no longer there. And the one also occurring at around 5 seconds on your after, they have been eliminated. Okay, so there are multiples, but they will take the shape of your events, so they can be very confusing and all that. Now, in your stack section, before multiple elimination, if you look at this stack section, another way to attenuate multiple is we have what we call radon demultipling. Okay, radon demultipling. If you look at this, a typical stack section before and after radon application. If you look at the stack section, you see some horizontal events in this area that I put my green arrow. You see some horizontal events. So if you are not, if you don't know that they are multiples, you would think that they are geologic boundaries. You can see them. You think that they are geologic boundaries, but by the time the multiples have been attenuated using the radon demultipling module, you see on the right that those events, those horizontal events that are looking like geologic events, they have been attenuated. So these are the things. So why do I bring this up? During interpretation, if the processing is not properly done, you are at risk as an interpreter, because you will be looking at, for instance, data with multiples. You'll be looking at the multiple and you think they are events, and you go and be mapping it as a geologic event. But in reality, they are not geologic events. So I don't know if that makes sense to you now. So finally, on noise, this is a typical stack section before noise attenuation. Look at this stack section. Before noise attenuation, you can see the strong amplitude. These are your ground rules, this strong amplitude, and a lot of other noise on the data. After they've attenuated the noise in the data, send it to different noise attenuation modules, this is what the result will partially look like, or will almost look like. Before, after, before, after. Also look at the frequency spectrum. Before, the frequency spectrum on the left, the one on the left. Before, you see the frequency spectrum, your high spiking ground roll noise, and other spikes and low amplitude of on the higher frequency part. Now, if you do your noise attenuation, see the frequency spectrum becomes improved. Okay, there are still some background noise in the seismic data. That's why you see the spikes. Okay, but typically, when you finish your noise attenuation, your data becomes improved in this way: before, after, before, after, before, after noise attenuation. I hope that is understood. Are we on the same page now?
Yes, sir.
Good. So this is the importance of noise attenuation on your seismic during processing. So you are trying to eliminate this noise. So before you remove noise, you can see this is a stack section, more or less a cross section of the subsurface. You are not seeing any of the events. You're supposed to be seeing the flat events, which are mimicking the geologic boundaries, but you are not seeing them. Why? The noise is masking your data. But by the time you run through different noise attenuation modules, depending on the noise you identified in the data, you begin to see your events more continuously. Okay? Moderator, do you still have like 20 minutes?
Yes, exactly 7:40.
Okay, so in the next 10 minutes, I'll take you through another processing step called amplitude compensation. Now, if you look at this data critically, this task section, you find out that the amplitude from here, 0 milliseconds to maybe about 2.5 milliseconds here, amplitude is very high or relatively high, right? You can see the data, your events, okay? Layer by layer in terms of peak and troughs. But from here down to here, are you seeing any events from maybe 2.5 seconds to 6 seconds? Are you seeing the events? Nothing. The amplitudes in this area is, the amplitude of the data is low, very, very low amplitude, while you have high amplitude in this part. So why is that? Why do you have amplitude, high amplitude in the shallow part of the data from 0 to maybe 2 seconds, 3 seconds and thereabouts? And as it progresses down into the data, the amplitude, the data becomes like it's white, it's whitening out. The amplitude are no longer there. Why? That is why do you have that? We have that because amplitude is lost with depth. As the seismic wave travels away from the source, it loses its energy. Okay, as the seismic wave is traveling from the source on the surface down to depth in time into the subsurface, it's losing its energy. And so this shallower part where the seismic wave is very strong, amplitude will be high. And as it travels deeper down, the amplitude will be low. So what do we now do? After you finish attenuating noise in your data, you have to compensate for lost amplitude. So in a process called amplitude compensation. So if you hear them talk about amplitude compensation, you are trying to compensate for lost amplitude, okay, in the deeper part of the data. And if you also look, this part of the data where I circled green is looking low. The amplitude here is also low. So you need to balance your amplitude throughout the data horizontally and vertically, okay? So you need to do amplitude compensation. So I've just explained myself. When the seismic wave is traveling from the source, spiraling away from the source, okay, what happens is that the energy is lost as the seismic wave travels away from the short point. Energy is gradually lost as distance away from the short point increases. So why do energy get lost? Okay, why do we even do this amplitude compensation? How and why is the energy lost with increasing distance? Number one, spherical divergence. We look at the short gather on the right, at the shallow part from here to 3 seconds, 3.5 seconds, amplitude is relatively high. But from 3.5 seconds to 6 seconds, 6.5 seconds, everything is looking whitish. Amplitude is lost. Why? Spherical divergence. As the seismic wave is traveling from the source point to the receiver, down into the subsurface, as it's spreading away from the source, the energy is lost. How do I mean? If you're in your house and somebody is in the room with you, if he plays a loud music, you hear him very well. He's playing the music, right? You're hearing the sound of your Bluetooth, your speaker is playing. By the time you move from your room to somewhere else, maybe the next flat, you stop hearing the music loud. Why? The distance from the source of the music has increased. So the music is dying, the sound wave is dying out as it travels away from the source. So the same way, when you have seismic wave spiraling away from the source, it loses its energy. And the process is what we call, the process whereby the seismic wave is spiraling away from the source is known as spherical divergence, okay? So an inverse of the distance time of travel, reduce in terms of the square root of the radius, inverse of the square root of radius or square root of the time of travel will give you what? Your spherical divergence. Your energy will be lost with increasing distance or increasing time. So that's one way of losing the energy of your seismic data by spherical divergence. Another way your seismic data loses its energy is what we call transmission loss. Remember, when we talked about reflection, seismic reflection, we talked about V1, density 1, velocity 1, density 2, velocity 2, right? We use it to calculate what? What did you use this formula to calculate? These parameters to calculate. Your V1, your density 1 and velocity 1 gives you acoustic impedance. Yeah, your acoustic impedance. Okay? And then we use it to calculate what? Reflection coefficients. Remember, where you were able to use your reflection coefficients to generate a seismic trace. Remember that small assignment we did sometime in the beginning of this class. What happens is this. Your seismic wave, when it travels from this source and it's traveling downwards, on getting to this boundary, what happens? It is reflected. We already all understood this part. No need to waste time on that. And then it's reflected back to the surface. The reflection is dependent on the reflection coefficient. So if your reflection coefficient is 0.0, you remember the assignment we did now, 0.02, for instance, it means that let's assume that the seismic wave on generation from the source, it's 100% of the energy that is traveling. Okay? On getting to this boundary, 0.02% of that energy is reflected. Okay? So what will be left? What will be left will be 99 point something percent of the seismic wave. So what will be transmitted will be 99 point something percent. On getting to this boundary, assuming that reflection coefficient on this other boundary is 0. Maybe 3, okay, due to strong events. And what will happen? You will say 99.8 something or whatever, 9 something, you remove that's transmitted to this point, you are now going to subtract 0.3%, which is the reflection coefficient at this boundary. So if you keep repeating that process, remember that in the subsurface, there are multiple thousands of geologic boundaries, okay, or rock boundaries. So as the seismic wave keep traveling downwards, on getting to each of the boundaries, there will constantly be what? A reflection, okay? And each of the reflection, based on the reflection coefficient, will extract some amount of energy from the transmitted seismic wave, okay? So in other words, you say that there is what we call what? Transmission loss. So the transmitted seismic energy will keep losing its energy or keep losing itself anytime there is a reflection, okay, at the geologic boundary. So with increase in depth or increase in travel time and increase in number of reflecting points, reflecting boundaries in the subsurface, the energy of the wave will continue to die out. So transmission loss is another way that your seismic wave loses itself or loses its energy as it travels down with time, increasing time. The last one is that another way you lose the seismic energy with increasing time is absorption. What do we mean by absorption? If the seismic wave is traveling through the rocks acts as a filter of the seismic energy, okay, that we'll talk about in the convolution. And not only is it acting as a filter, it absorbing the energy of the seismic wave. So the seismic rock absorbs the energy. More or less, it's like you get a mail today that says that you won a scholarship or maybe you won a lottery. And out of excitement, you start shouting and shouting and shouting. What happens? Everybody is hearing your voice. But let's assume you don't want to shout so that your neighbors will hear your voice, or you don't want your brother or your sister or your mom or your dad to hear your voice. What do? You put a pillow over your face. So what does that pillow do? The pillow will absorb the sound wave. So you put a pillow over your face and you scream in excitement that you won a scholarship or you won a lottery or whatever. The pillow will suppress your voice. So nobody will hear that you scream. But in actual sense, you actually screamed very loud. You screamed out your voice. But the pillow didn't allow the voice to go out. So that is the same thing that happens in the subsurface. As the seismic wave is traveling down into the subsurface, the rocks are absorbing the energy, okay, of the seismic wave. So another way that the energy of the seismic wave is lost is through absorption by the rocks, okay, the subsurface rock. And while doing the absorption, the seismic energy, while absorbing it by the rocks, a small amount of heat energy is being generated. So because the seismic wave while traveling is a mechanical energy, is in motion. So impacting or having impact with the different rocks as it's traveling through them, small amount of energy is generated, okay? And that energy is heat energy, okay? So the absorption by the rock is known as Q. So during amplitude compensation, that's what they put into consideration called the Q compensation, okay, or the Q factor. They put the Q factor, which is the absorption factor of the rock. Now, the Q of different rocks varies. So the way different rocks absorb the seismic energy differs, okay? Now, absorption is dependent on frequency. The higher the frequency of the seismic wave, the faster the seismic energy will be absorbed. And the lower the frequency, the slower the energy will be absorbed. For instance, on the pictures on the images on the right, or the graphs on the right, you have the low frequency on the one on the top, on the upper part. So if you generate seismic wave with an amplitude of 1 decibel, okay, at a point 0, okay, and let's say the seismic wave is just 5 hertz, okay, which is low frequency, and the absorption, what is the Q factor of that rock, let's say it's a sandstone, is 50, for instance. Because the frequency is 5 hertz, by the time the seismic wave travel from 0 point to 4,000 meters away from the source point, so this is the source. The source is at 0. So by the time you get to a receiver that is 4,000 meters away from this source, which is receiver R, the seismic energy will still have enough amplitude. The amplitude will be about what? So somebody read up this graph for me. The amplitude will be about what?
5.
It's at 0.5, not 5.
0.5, yes. 0.5.
Yeah, 0.5 decibels. So for low frequencies, remember I told you that the low frequency waves, they travel further into the subsurface. I told you some time ago in one of our classes. And the low frequency seismic waves, they are less absorbed by the rocks. So they will travel further and further and further. So with 4,000 meters of travel, the low frequencies still have amplitude of up to 0.5 decibels. So they are still visible. But your high frequency, on the other hand, high frequency of 50 hertz with the same Q factor of Q compensation factor within the rock, let's say it's a sandstone unit, high frequency 50 hertz. If you generate the seismic wave on a source located at 0 point, by the time the seismic wave travels to 2,000 meters, which is receiver located at 2,000 meters away from the source, at 0 point where the source is, the amplitude of the wave is 1 decibel, for instance. By the time you get to 2,000 meters away, because it's high frequency, what happens? The frequency is almost what? Somebody talk. Yeah, 0.1 or 0.0 something. It's not even up to 0.1. 0.1 is in the middle.
0.05.
Yeah, something like that. So by the time the seismic wave travels 2,000 meters from the source, it has lost almost all of its energy. Why? It has high frequency. So in other words, the takeaway here is that when they're acquiring seismic data, remember I told you they have to acquire high broadband seismic data from 1 hertz, okay, to 240 hertz, or 250 hertz rather. 250 hertz. That's your conventional seismic acquisition. That's the frequency bandwidth. So they acquire all the frequencies so that the low frequencies will travel far into your subsurface, while the high frequencies, they will die out quick. And they do that because of what? Absorption. Absorption has an effect of the rocks, attenuates your seismic wave. So to compensate for those seismic wave the energy that has been lost through these 3 points, through our spherical divergence, transmission loss, and absorption, you need to compensate for those lost amplitude at great depth. So what happens? You do an amplitude compensation process on your module, on your seismic data. So for instance, this is your short gather after you have attenuated noise from the data. looking at it now, you see that from here to here, amplitude is relatively high. Okay. From this point down to this point, amplitude is low. So you need to balance this energy. What do? You balance it out. The upper part will still have a relatively high amplitude, but the lower part will increase you can start seeing events in the deeper part of the seismic data. This is for a short gather display of short gather amplitude compensation on short gather. Another way you do that on your stack section. This is stack section before amplitude compensation, which is your stack section after noise attenuation. When you balance the energy, you can see that at deeper part, here, you're not seeing anything. Everything seems whitish, okay? But by the time you increase the amplitude, you're beginning to make out some events, okay? And then on the shallow part, you see this part that was initially on the shallow part that has low amplitude. While you do your amplitude compensation, everywhere seems to be balanced out. So that is the essence of doing amplitude compensation on your seismic data. You're trying to balance the energy after you have lost some of the seismic energy due to transmission loss, spherical divergence, and absorption by the rocks. So that is the essence of doing amplitude compensation. So there's fundamentally the process or the reasons why you do amplitude compensation. So you can be hearing things like surface consistent amplitude compensation, horizontal balancing, whatever terminology they are using. This is the fundamentals behind it. Is there any question from here? So furthermore, this is another amplitude compensation. Before, after, before, after, before, after. You see the effect of amplitude compensation. Before, the amplitude, the higher energy is on one side of the data. When you compensate, you spread out the energy across the whole data so that everybody, every event becomes more visible. Yeah, go ahead.
I say sorry to interrupt, but yeah, I want to tell you it's 4 minutes to 8.
Okay, so I think I'm done. By next time we'll talk about the conclusion. Okay, then velocity analysis and migration. So I think we'll call it a day here. We were right on time. So that's it for today and intro about seismic processing, which I want you to have an idea of before we go into interpretation. Any questions so far? I don't think we'll have time to entertain question. Any question can be sent on the platform. I will attend to it on the platform. So we can call it a day from here. Thank you so much for your time.
Thank you very much.
Yep.
Thank you, sir.
Okay. Okay, good night from me.
Okay, good night, sir. Good night, everyone. Thanks for coming. Thanks for your time, everyone.
Okay.
Thank you, sir.